C-MobILE, Accelerating C-ITS Mobility Innovation and Deployment in Europe. E-learning course on C-ITS. Part 3. Public Authorities. Project co-funded by the European Union. Authors Evangelos Mitsakis and Ariti Kotsi. From Surf HIT. Giacomo Sommer from Ertico, ITS Europe. This training is aimed at three main categories of public authority staff: operators of traffic management centres, technical staff, and maintenance supervisors. The purpose of this training is to provide these three target groups with a general knowledge about cooperative intelligent transport systems and services, with some more in-depth details as compared to what has been shown in Part 1 of this training. An understanding of the various components of cooperative systems, their functionalities, interactions, and integration, and some basic skills needed for the deployment and operations of C-ITS services. In addition, this training aims to enable the operators of traffic management centres to understand how to exploit C-ITS technologies, connecting the road infrastructure and the road users, to understand which data are exchanged by means of such technologies, and which cooperative mobility services can be deployed, and to understand how to integrate technologies, data, and services in traffic management centres by means of new or updated IT platforms. By doing so, this e-learning course also aims to increase the replication possibilities of C-ITS technologies in European cities in order to increase transport safety, efficiency, comfort, and sustainability for all road users. Before explaining in detail what C-ITS technologies are and how they can be used to improve traffic management, it is important to define some basic terminology and steps to make sure we have a common understanding. The first step for a public authority is to formulate the objectives and the results to be achieved. These can be then translated into a series of policies. A policy defines the way and the course of action to be adopted in order to achieve the objectives and deliver the expected results. On this basis, it is possible to develop a strategy in which are defined the approach and detailed plans to implement the policy. Let's see two examples of how mobility objectives can be translated into policy options and implementation plans, with a specific focus on how C-ITS can be part of the solution. In the first example, from the city of Barcelona, the objective of the public authority is to reduce traffic congestion and emissions. To achieve this objective, several policy options may be considered, such as traffic restrictions for some types of vehicles, or incentives for some other transport modes, and the deployment of a C-ITS solution, like the Glossa service. The choice of policies requires the policymaker to assess what is practically feasible and acceptable. The deployment of the Glossa service could require an improvement and adaptation based on its actual impact on traffic flows. This service could, for example, be implemented in a specific area and for selected users, like a public bus travelling along a road without a segregated lane. Once the impact is clear, the next step would be to extend the Glossa service to the entire road network and to other users, possibly combined with priority criteria for certain user categories over others. The strategy to implement such a solution could encompass the identification and engagement of key mobility actors and service providers, the adaptation and the upgrading of the traffic management centre through the integration of C-ITS technology, and the provision of traffic data and advices by means of an end-user app. In the second example, from the city of Copenhagen, the objective of the public authority is to promote cycling and the use of public transport in the city. To achieve such an objective, the policy options could involve the introduction of incentives to increase the convenience of the citizens to opt for such transport modes, and tolls for vehicular access to the city. This could be achieved by introducing new services based on the use of data from multiple sources, which in turn require standardized data and solutions. The plans and tools to be implemented would include several actions. For Copenhagen, they would include the deployment of the physical and digital CITS infrastructure on the road and in the cloud, the integration of different data sources, the development of an end-user app, and the setup of cooperation agreements with other public authorities at regional and national level. Let's have a closer look at the various elements and steps for the development of an urban mobility policy. Having in mind the example of the city of Copenhagen, wanting to promote cycling and public transport use, the policy development process may include: first, the development of a strategic plan with tangible and measurable targets, such as number of users and trips made by bicycle and public transport, and the corresponding reduction of emissions. Second, the engagement of stakeholders and vendors from the whole transportation and mobility value chain is a key element in the perspective of a multimodal transport system, because the mobility issues do not stop at the administrative borders of a city. In this perspective, it is important that the needs of various end users are identified and that data from various sources are shared and integrated to create a well-balanced value for the different user categories: the citizens, the businesses, and the public authorities. A third aspect is the matching of policy goals versus emerging trends in terms of technology standards and regulations. This is needed to define a detailed plan for the implementation of the physical infrastructure, like the roadside systems, and the digital infrastructure, such as the cloud services. In addition to that, it is important to define the means to promote the services' uptake by the users, such as economic incentives, soft nudging measures, or gamification techniques. It is then important to analyse the existing conditions within the city. This involves the engagement of local public and private actors, and the matching of their respective needs with the overall policy goals. At the same time, it is important to create and gather data from existing or new sources in a standardised way. Last but not least, it is important to ensure the commitment of all key stakeholders and availability of sufficient resources for the policy implementation. From a technical point of view, this may require the integration and consolidation of various systems and their elements, including the updating or upgrading of legacy systems. It is equally important to gather commitment from institutional and business actors and inform all users and actors by creating awareness and information campaigns through different communication media. According to the guidelines developed by the European Commission, a Sustainable Urban Mobility Plan, in short SUMP, is a strategic plan designed to satisfy the mobility needs of people and businesses in cities and their surroundings for a better quality of life. A SUMP considers the whole functional urban area and foresees cooperation across different policy areas, across different levels of government. And with local residents and other principal stakeholders, it ensures a variety of sustainable transport options for the safe, healthy and fluid passage of people and goods, with all due consideration for the residents and the urban environment. The European Commission strongly recommends that European towns and cities of all sizes should embrace the SUMP in defining strategic plans for implementation of urban mobility policies. On the ELTIS portal, you can find reference guidelines and briefings that have been published by the European Commission for policymakers, urban planners, and practitioners in the field of transport and mobility. The guide related to the role of ITS in SUMP is available at the link indicated on the screen. Let's now have a closer look at the third step. Once the policy is developed, it is possible to define the strategy to implement CITS solutions in the city setting. Such implementation should include the elements and steps displayed on the screen. The initiation of the project planning process, which includes the identification of different phases, achievements, and means of verification. The establishment of a cooperation with the industry. The adaptation of the reference CITS architecture to the local needs and characteristics of the city. The detailed description of the services to be deployed, the technology, and installation traits. The involvement of end users for CITS services, starting from local fleet operators of shared and public transport, logistics and delivery services, but also individual road users, such as motorists, cyclists, and pedestrians. Activities related to procurement for installations, operations, and maintenance. Let's see an example from the city of Thessaloniki of CITS deployment strategy and corresponding implementation steps. First, a preliminary study was conducted to identify which roads are mostly affected by traffic congestion, accidents, and parking issues, in which the deployment of CITS services is likely to improve mobility for businesses and citizens. Then, a cooperation was sought between the Traffic Management Centre and other local technical partners, including transport and fleet operators, to define and execute the CITS services implementation plans. The existing systems and infrastructure in the city were then updated and adapted according to interface with a common reference architecture to ensure interoperability. The technical and functional specifications of the cooperative systems and services to be implemented were also designed while identifying the locations in the road network where the physical and digital infrastructure had to be deployed. The recruitment of end users for the services operation was carried out by establishing a collaboration with taxi fleet operators and by recruiting university students and staff and the general public. Once the services and the end-user application were successfully tested during the experimentation phase, the activities related to their operation and maintenance were started. This is needed to ensure that the CITS services deployed will continue operating properly, with the expected level of quality and reliability, and that it is possible to implement future upgrades and extensions. As explained in Part 1 of this e-learning course, CITS stands for Cooperative Intelligent Transport Systems. This is defined as a group of technologies and applications that allow road users to exchange data with each other and the surrounding digital road infrastructure through wireless communications. This digital connectivity enables a wide range of information and cooperation services that allow road users and traffic managers to interact and coordinate their actions, helping them to take the right decisions and to adapt to the traffic situation. Wireless communication technologies used in CITS can be classified into short-range, ETSI ITS G5 radio broadcast, which provides low latencies, useful for time-critical messages. Long-range, cellular networks, which provide wider coverage and scalable access to a large number of devices. These technologies complement each other and can be used together in a combined, hybrid way. At this point, it is important to understand that, in order for a citizen or a road authority to use a technology, it is essential that it works correctly everywhere and at all times. For this reason, CITS technologies and services need to be standardized and interoperable independently from the technology vendor or the service provider. Whether this is about traffic safety and efficiency, navigation systems, parking assistance, roadside assistance, remote diagnostics, telematics, infotainment, automated self-driving vehicles, or mobility services on demand. In particular, wireless communication technologies used for CITS are based on standards, which are developed by various organizations. Among them, the European Telecommunications Standards Institute, ETSI, the European Committee for Standardization, CEN, the International Organization for Standardization, ISO. Several message sets used for CITS applications are also standardized. The main ones are the Cooperative Awareness Message, or CAM. This is a message sent by a vehicle 1 to 10 times per second with information on the position, direction, and speed of the vehicle. This is a way to say, "Hi, I'm here." The Distributed Environmental Notification Message, or DENIM. This is a warning message sent with high priority to a vehicle based on information from other vehicles or the road infrastructure. This message is used to inform road users about slippery conditions, accidents, and other road hazards. Signal phase and timing, or SPAT. This information is sent by the controller of the traffic light to the road users about the traffic light status, green, yellow, or red, and its future changes, such as how many seconds are missing for the red light to turn green, and vice versa. In-vehicle information, or IVI. This message set is used to present the physical road sign on the screen of the navigation system of the vehicle, such as speed limit or stop sign, including the variable message signs typically showing information about travel time or road hazards, like accidents, works, or lane closures. Map message, which describes the physical geometry of an intersection. Those are the most common message sets that the road authorities use when implementing CITS services. Others are also available based on common standards, like Point of Interest, or POI, and Datex 2. In this e-learning module, we will not go into more details, because there is a vast literature on these matters, and because standards are continuously evolving. In this evolution and in new developments, two aspects to consider are the technology retrofitting and the backward compatibility with previous standards. This is very important for the public authorities, although it is understood that some innovations cannot be compatible with older, obsolete technologies. Another aspect to be considered is that the deployment of cooperative systems and services requires the support of a unified architecture framework. This can be seen as the set of interface structures, rules, and systems connected and working together. Each structure comprises software elements, relations among them, and properties of both elements and relations. The conceptual scheme presented here is intended to provide an overview of a reference architecture framework, without going into the details of its specific elements, with their dependencies and responsibilities, and without describing the detailed functions, interfaces, and interactions. In this scheme, the CITS architecture framework is presented from 6 viewpoints: enterprise context, functional, information, implementation, physical, and communication. The implementation view describes the implementation for realizing functionality into real-life software systems. This allows building, testing, maintaining, and enhancing the system. The functional view describes the runtime of the functional elements of the system, their responsibilities, their interfaces, and their primary interactions. This helps to understand the structures of the system and has an impact on the quality of the properties of the system. The context view describes the relationships, dependencies, and interactions between the system and its environment. That is to say, the people, the systems, and the external entities interacting with the system. The physical view describes the physical environment where the system will be deployed, and the dependencies that the system has on elements of that environment. This allows deploying, testing, and maintaining the system by capturing the hardware environment that the system needs, the requirements of the technical environment for each element, and the mapping of software elements to the runtime environment that will execute them. The communication view describes the communications between different subsystems deployed on different hardware environments, such as the interfaces and the communication protocols. This allows defining and enabling the communication between systems. The information view describes how the architecture stores, manages, and distributes data and information. It provides a high-level view of static data structure and information flow to users, developers, testers, and maintainers. The design of a system's architecture shall ensure the following principles. The interoperability, which is the degree to which two or more systems can exchange data and information and use it. The security, which is the degree to which the system protects the data and information exchanged. The performance efficiency, which represents the balance between the resources consumption and the services provided. The usability, which is the degree to which the system can be used to achieve specified goals. The reliability, which represents the ability of the system to perform the right functions under specified circumstances. The availability, which is the degree to which a system is accessible and operational. The adaptability, which is the degree to which the system can adapt efficiently and effectively to different or evolving hardware and software environments. As more vehicles equipped with C-ITS services hit the roads, software vulnerabilities become accessible to malicious hackers using cellular networks, Wi-Fi, and hardline connections to exploit them. The potential for hackers to gain unauthorized remote access to the vehicle network and compromise critical safety systems puts at risk not just users' personal information, but their physical safety as well. Such threats have created the need for broad-scale secure key management, supported by a public key infrastructure, PKI. A public key infrastructure, PKI, is a set of policies, hardware, software, roles, and procedures needed to create, manage, distribute, use, store, and if needed, also revoke digital certificates, and manage public key encryption. The purpose of a PKI is to facilitate the secure electronic transfer of data. Pseudonymization is a data management and de-identification procedure by which personally identifiable information fields within a data record are replaced by one or more artificial identifiers or pseudonyms. A single pseudonym for each replaced field or collection of replaced fields makes the data record less identifiable, while remaining suitable for data analysis and data processing. PKI solutions provide the infrastructure that enables entities to establish trust relationships between each other, based on their mutual trust in the Enrollment Authority, EA. The Trusted Certificate Authority issues a certificate of identity, which enables the registration of a vehicle with the public key. The certificate is valid over a long period of time, and it is registered in the Enrollment Authority, identified with the initials EA. Peer entities that trust the Enrollment Authority can trust the certificate, because they can verify the authority's signature. So they rely on the information in the certificate, the most important of which is the association of the entity with the public key. The enrollment certificate is combined with an authorization ticket, also known as pseudonym certificate, that is the mask in our example. This ticket allows the vehicle to obtain permissions to communicate with other vehicles. Tickets are managed by another authority called Authorization Authority, or also known as Pseudonym Certificate Authority, identified with the initials AA, and renewed on a regular basis to preserve privacy and avoid traceability of the vehicle and its user. This way, the Enrollment Authority can identify the vehicle, but not trace it, while the Authorization Authority can trace the vehicle to some extent, but not identify it. When a vehicle requests a new ticket, the request is signed with the vehicle's private key. As the corresponding public key is registered in the Enrollment Authority beforehand, this is able to know if the request is made by a registered vehicle or not, and if yes, by which vehicle. The authorization tickets provided to the vehicle, also known as pseudonym certificates, are signed by the Authorization Authority, and each ticket contains the identifier, hash of the signer. The receiver vehicle gets the list of trusted certificates from the Authorization Authority. When it receives a message, it checks that the ticket is valid. That means that the signature is correct and that the signer hash is belonging to the trusted certificates list. If both conditions are met, it means that the receiver is sure that the message is issued from a trusted vehicle. When the enrollment certificate is revoked by the enrollment authority, the authorization authority will also make void the authorization tickets, with the creation of a sort of blacklist. In this case, the sender vehicle is not authorized anymore to communicate with other road users, and the receiver vehicle will not recognize the message as trusted. The same process applies also for the exchange of certified messages between any vehicle or road user and the road infrastructure. This is valid with some differences whether the communication happens via ITS G5, as shown in this scheme, or via cellular network. Traffic management is the organization, arrangement, guidance and control of both stationary and moving traffic, including pedestrians, bicyclists, and all types of vehicles. Its aim is to provide for the safe, orderly, and efficient movement of persons and goods, while protecting and, where possible, enhancing the quality of the local environment on and adjacent to traffic facilities. Traffic management information are aimed at providing guidance to road users on the conditions of the road network and of the traffic, at the monitoring of incidents and emergencies, and the timely implementation of response strategies for safe, efficient, and optimal use of the existing road network infrastructure, including beyond borders. Such information includes road and traffic conditions, speed advices and limits, variable message signs, including parking information, weather conditions, hazard zones, such as work zones, other road events, either unforeseeable or planned, such as accidents, lane closures, strikes, demonstrations, major public events, holiday traffic peaks, or other capacity overload. To ensure that traffic management information and contingency actions provide for a safe use of road infrastructures and a smooth flow of traffic, road operators are responsible and should be competent and effective on imposing the appropriate rules and prohibitions for safety, quality of life, and traffic flow, providing timely warnings in cases of dangerous and abnormal situations, informing and advising road users about known events, alternative routes, and alike. There are three main approaches that can be adopted on traffic management: a static, a responsive, and a proactive management of the traffic. These three approaches escalate from the least to the most complex one in terms of actively managing operations and respective risks. More specifically, a static management of traffic is applied with regards to the time of day, and measures are set, since variability in the condition of the network is limited. A responsive management of traffic is applied with regards to current conditions, and takes also into account the impact of traffic to the condition of the network. The main purpose of this approach is to reduce the time of degraded operation. Finally, a proactive management of traffic has the objective to respond to predicted changes in the road network capacity against the demand. The advantage of this approach is the possibility to delay or eliminate possible and foreseen breakdowns. Depending on the traffic management approach, different governance frameworks can be adopted. In this image, you can see three levels of traffic management application, each one of them connected to both the road authorities and the road users. Beginning with the higher level, where the policy focus is on the network, the objective of the traffic management approach is to intervene in the network flows and manage to shift them, in order to achieve traffic flows optimization in the entire network. Moving to the road segment level, the objective is to optimize the flow in this specific section of the network. Finally, the lowest level is related to users, who are the actual travelers in the network, and the objective of a related traffic management approach could focus on the provision of personalized traffic information. Nowadays, traffic management is considered to be in a state of transition because there are many challenges to be addressed to keep up with new mobility trends and fulfill multiple policy goals. Among others, current challenges include handling congestion triggered from increased mobility, reduce significantly road accidents, according to the EU Vision Zero policy on road safety, achieving agreed goals on sustainability, environment, and climate, as defined in the new EU Green Deal strategy, managing mixed traffic, and integrating new technologies into typical traffic management processes. The modern perception of traffic management is comprised of four main pillars: the exchange and use of growing data streams from multiple sources, the development of new assets related to smart infrastructure, the possibility to influence behaviour of road users and mobility patterns, and a strong cooperation and coordination among all involved parties, which are needed to enable network optimization. In this context, it is clear that CITS can bring various benefits for public authorities. On one hand, CITS can enable a more efficient traffic management in terms of improved management of the road transport system, a smoother traffic flow, and an increased safety. On the other hand, CITS can support policy goals such as reduced harmful emissions and congestion, increased road safety and security, higher local innovation and growth, and a more livable city in terms of accessibility, sustainability, and inclusiveness. In addition, CITS can improve the overall performance of transport operations in terms of reduced travel times, higher journey time reliability, priority for selected users, such as emergency vehicles, public transport, and vulnerable road users, reduced costs of transport in terms of energy or fuel consumption, and operations efficiency. Finally, as already mentioned, CITS can support the delivery of the European Vision Zero and new Green Deal policy objectives set by the European Commission with specific targets to be achieved by 2030 and 2050. The integration of CITS into a traffic management centre's environment constitutes a recent innovation for which many prerequisites need to be met. As with any innovation, the integration of CITS services into traffic management centres addresses different stages related to acceptance, such as denial, experiment, decision, and finally integration. An effective way to avoid the first initial negative stages would be to define the prerequisites. These are comprised of availability and adequate density of real-time dynamic data, willingness and ability to embrace new approaches, appropriate business and partnerships models, adequate perceived benefits for both TMC operational capabilities and transport network performance. In the era of connected and cooperative mobility, new roles and functions for the traffic management centres are emerging. The TMC functions will continue to rely on traffic engineers, but the roles and expertise of the TMC staff will be redefined in order to deliver all the advantages enabled of CITS technologies. The integration of CITS in a TMC environment will bring access to new data and information sources, increased situational awareness of the transport network, including parts outside of the TMC own responsibility, awareness of the impact of CITS-enabled traffic control strategies on traffic performance and road user acceptance. Automated, targeted, and personalized information will be provided to road users. There will be new capabilities for supporting long-term planning based on precise information of mobility patterns, and there will be increased accountability for activities, use of resources, coordination with external parties, as well as overall system and network reliability. The information currently available to traffic management centres from roadside infrastructure, such as traffic lights, basically includes their status, control, and location. CITS can enable the exploitation of additional information, including the integration status, the required system uptime, the new technology systems with new types of data, and various performance metrics. The changes to the TMC operational processes therefore include a higher uptime and integration level of devices, the reporting of the performance and the management of the status of a field device, automated alerts and troubleshooting, the monitoring assets and tracking issues based on performance, and an improved management of the life cycle of the equipment. In this video, you can see the dashboard of a traffic management center enabled with CITS technology to monitor the green and red phases of traffic lights in a city, but also how these can be managed dynamically to give priority to a public transport bus equipped. Thanks to CITS, it is possible to visualize all the equipped traffic lights in the city, to connect to and diagnose each traffic light controller, to exchange functional messages and alerts, to display a satellite image of the intersection with the various trajectories and their congestion level, or the functional view of all the equipped infrastructure, such as traffic lights, road sensors, cameras, etc., to manage each device on the field by means of a dashboard. The speed-related information currently available to traffic management centres includes the traffic volume, road occupancy and speed limits, video camera information at certain spot locations, lane by lane, traffic flow directions with limited movement and tracking information, robust historical data, and traffic congestion status on highways and main arterials. CITS technologies enable the exploitation of a lot of additional information, such as density and contextual information, broader road network coverage, continuous movement and tracking information, high data accuracy, specific metrics related to the vehicles and traffic, prediction of the impacts of different traffic management and operation measures. The changes to the TMC operational processes comprise reporting and real-time monitoring of state and performance of the transport system, congestion warnings, real-time information on the impact of the application of different traffic control strategies, and ubiquitous probe coverage that allows the monitoring and managing of larger road networks. In this video, you can see the dashboard of a traffic management center enabled with CITS technology to monitor in real time the road conditions and manage dynamically the speed limits. Here, 3 situations are shown: the speed control in a tunnel, a radar-enforced speed limit at 100 km per hour, and a warning message to slow down due to slippery road conditions. Events information that is currently available to traffic management centres includes date, time and length of the event, its impact on the local network, information about lane restrictions, such as closure, deviation, or traffic inversion, and limited monitoring of images and signal timing changes during such events. CITS technologies enable the exploitation of additional information, including situational awareness about the wider event location, impacts on the broader network, and multimodal traffic information, aiming modal shift to reduce congestion. The changes to the TMC operational processes comprise improved and advanced traveller information to support area accessibility during events, proactive management of events, advanced modelling of network response to traffic alterations, enabling predictive traffic management of network analysis, real-time management of multiple transport modes and mode shifting support, and reduction in required field resources to support events traffic management. In this video, you can see the dashboard of a traffic management center enabled with CITS technology, allowing the dynamic management of network and traffic events in a city, including traffic jams, various types of hazards, weather-related situations, and others. Among other details, this includes information about their start and end position, speed and direction, start and end time. Thanks to CITS, it is possible to visualize all the physical and virtual variable message signs and points of interest present in the city, to activate or deactivate, verify and update to each virtual VMS. This includes sharing and editing information about the parking areas, their status, open or closed, related access restriction, if any, applicable tariffs, number of available places, and finally booking possibility for parking offering park and ride services in connection to public or shared transport. Weather-related information currently available at traffic management centres includes pavement conditions like icy roads, atmospheric conditions such as rain, snow, wind or low temperatures, and real-time alerts and forecasts. CITS can enable the exploitation of a lot of additional information, including more precise information about the conditions of the road pavement, including slippery conditions due to spillover of liquids from vehicles or degradation of the asphalt, the impact of weather conditions on the road and traffic flow, like in the case of a sudden fog bank, numerous safety-related information. For each situation, CITS technologies allow to assess the numbers of vehicles concerned, the extent of the impacts, the vehicle and traffic metrics related to a specific weather situation, and prediction of estimated impacts. The change to the TMC operational processes allow to provide immediate real-time warnings, advanced warnings on impacts, better and up-to-date notifications, and decision support for road weather response teams. In case of bad weather conditions, traffic managers can create an alert on the ITS dashboard of the Traffic Management Centre, which is immediately transmitted and presented to road users through the physical road infrastructure, that is to say, the variable message signs installed on road gantries. CITS technology also enables traffic managers to send alerts directly to the road users. In this case, the virtual messages are presented through the so-called digital infrastructure. For drivers, this means an icon or sound on the smart dashboard of their connected vehicle, while for other road users, this means a smartphone or other smart connected device. Real-time and predictive alters can be created by traffic managers, so that road users can be informed of bad weather events before they reach the area where they are occurring, or even before the event actually occurs. For instance, this is the case of areas where there are fog banks, or where there is a risk of slippery road conditions due to heavy rain or very low temperatures. The information related to work zones that is currently available to traffic management centres includes surveillance and lane restriction updates. CITS enable the exploitation of additional information, such as adherence to speed restriction, monitoring of vehicle manoeuvring, real-time lane restriction, and traffic and control verification and violations. The changes to the TMC operational processes allow for the provision of timely advisory warnings to travellers in the proximity of a work zone and the surrounding areas, improved safety warnings when approaching or within a work zone, dynamic warnings about speed and lane restriction, modification of work zone implementation strategies based on traffic response, and traffic control violation notification. In this video, you can see the dashboard of a traffic management centre enabled with CITS technology, allowing the dynamic management of work events in the road network. This includes information about their start and end position, lane and direction, start and end time, and the source of the information. Thanks to CITS, it is possible to visualize all the roadworks and more in general the events in the road network, to create or remove events, and to visualize and modify the status of each event. Incidents-related information currently available to traffic management centres includes their location, start time and end time, their duration and their severity. CITS enables the exploitation of additional and advanced information and capabilities, including the integration of geolocalization technology for precise incident location, the real-time collection and management of information about lanes restrictions, types of vehicles, and people involved. New capabilities for real-time and predictive assessment of impacts on the specific road stretch and on the wider network. The assessment of the need of divert traffic and the provision of alternative routing options. The real-time monitoring of the response status for fast incident clearance. In case time-critical interventions are needed for safety reasons, to rescue people and save lives, CITS enables a more efficient intervention by the police, rescue and emergency services by providing them with the best routes, while rerouting normal traffic by triggering alert messages to other drivers so that they can give way and facilitate their passage in a timely way, and by providing emergency services with green priority at traffic lights. The changes to the TMC operational processes involve real-time information on an incident and its clearance, better network management by enabling to mitigate impact of incidents and to minimize transport and traffic disruptions, enhanced response capabilities by using the appropriate resource and equipment, improved traveller notification, including for nearby arterials, advanced assessment of the causes of an incident, and of the measures to be adopted to improve transport efficiency and safety, and improved predictive modelling capabilities. New skill sets and credentials are required on information technology and data management processes for the exploitation of CITS technologies integrated in a traffic management centre. These skills include knowledge about hardware and software environments for big data and about the integration of management processes into the traffic management centre, expertise about data warehousing, queries and support for data access and redistribution, ability to support data management and sharing for policy development, ICT skills to integrate new software and related updates and upgrades, ability to coordinate with system developers and integrators to implement new traffic management centre systems and services. When it comes to systems analytics and processing, the new skill sets and credentials include the identification of how to update traffic management centre processes with new capabilities, the identification of what types of analysis can lead to improved operations and decision support, the understanding of how to coordinate with other traffic management centres or other agency divisions, and identify how new data can support their functions in terms of safety, planning, programming, project development, etc. The ability to aggregate and process data and to create metrics useful for performance assessment. The ability to analyse system and operational performance and recommended modifications based on outcomes. The skill sets and credentials required for network and device maintenance include maintenance capabilities for new field devices supporting CITS services, know-how for testing and deployment of new devices, ability to define technical specifications and requirements, and to coordinate with device vendors, ability to coordinate with IT and operations managers to integrate new devices into TMC processes. The skill sets and credentials required for operations engineering decision-making include specialised training for traffic engineering in presence of CITS, the ability to develop plans and strategies for dynamic and proactive management of traffic signal timing, which implies the implementation of modifications to signal operations to optimise traffic flow and safety in presence of CITS. The expertise needed to authorize and implement changes in strategies based on real-time and predictive CITS data inputs, such as weather response strategies, balancing network demand, or multi-agency corridor operations. Support skills for the development and active monitoring of system performance metrics, and the identification of where strategies need to be implemented to achieve performance goals. Understanding the benefits of CITS services and the required investments is a crucial step in the decision-making process of public authorities. As mentioned, the benefits of CITS deployment can be grouped in three main categories. The first category of benefits relates to road safety, which means reducing the number of accidents and fatalities, and at the same time the severity of collisions and the injuries and damages resulting from them. In addition, safety benefits can be provided through advanced coordination and dispatching of patrol, emergency, and rescue services. The second category relates to improving operational traffic efficiency, which means increasing the flow capacity of the road transport network, while avoiding or reducing the need for its physical expansion, and reducing the congestion and the disruptions due to incidents. The provision of real-time and predictive information about the road and traffic conditions, including planned and unforeseen events, enables a dynamic traffic management and an improved mobility planning. This can also lead to a higher level of service for citizens and businesses, reflected in the reduction of travel time and cost for all users, especially for fleet and commercial operators, while improving their comfort. In fact, CITS services can support a multimodal transport by providing real-time mode and trip advice prior and during a journey. The coordination with other local and regional authorities and with other managers of public services and utilities, combined with data sharing agreements with third parties, can enable responsive and proactive traffic management across various transport modes. Such coordination could, for instance, involve exchange of data related to maintenance services, construction sites, parking facilities, transport hubs at various levels, such as government to business or government to government. The third category relates to environmental benefits, which means reducing harmful emissions and reducing fuel or energy consumption. The exact measures of the impacts and benefits falling under each of these broad categories is not easy to quantify due to several factors, some of which are objective and measurable, while others are subjective and related, for instance, to local culture or user behaviour. A typical example is an urban area in which the services and infrastructure dedicated to public, shared, and active transport modes are limited in terms of geographical coverage, availability, or quality, therefore resulting in a prevalent mobility culture based on the use of private cars. CITS deployment is accompanied by certain costs categories. Being familiar with such aspects could help public authorities in the cost-effective and successful deployment of innovative CITS solutions. The various components necessary for CITS deployment relate to the installation, operation, and maintenance costs, and are associated to different stakeholder types, including the vehicle-to-vehicle and vehicle-to-infrastructure communication technologies, and the units of measurement. Traffic management integration includes the incorporation of CITS to existing traffic management centres and concerns mainly road operators. Roadside units are related to the number of intersections in which the equipment will be installed along the road network and concern road operators, original equipment manufacturers, and end users. In-vehicle devices costs are related to the number of onboard units to equip vehicles and concern end users and equipment providers. Personal devices costs are related to the number of smartphones and tablets to equip drivers and vulnerable road users, and concern end users and equipment providers. Data collection costs are related to the data necessary for the function of CITS and concern data providers and end users. Information about cost categories is given as an indication here. The actual cost of the various items is not quantified because these are determined by multiple factors. Among others, these factors include policy and regulatory aspects, the physical characteristics of the transport network, the level of development and use of the various transport means and modes, the level of interconnectivity of the local transport system, enabling multimodality, the presence and type of communication infrastructure for data provisioning and sharing, the costs of connectivity and communication services, and other market and pricing factors that vary from one region to another. As explained, the CITS bundling involves different objectives and provides different benefits, depending on the type end user. For the road users, these have been presented in Part 2 of this training course. For the public authorities, road operators, and traffic managers, the main objectives are: first, to extend the capabilities of traffic management centres by incorporating CITS services as tools for real-time traffic monitoring and control. Second, to create dynamic traffic management scenarios enabled by cooperative and connected systems. Third, to provide the ability to assess and tune CITS services in real time. And finally, to provide an easy-to-use and widely transferable software-as-a-service solution. The coordinated provision of CITS services can allow enhancing the traffic management, thanks to a bundling tool developed for road operators and traffic managers. This tool is made of two components. The first one, called the Scenario Manager, allows setting threshold and target values for each traffic control strategy, real-time monitoring of the road network and traffic status, and selecting, activating, or deactivating a number of control strategy settings and the associated CITS services. The second component of the CITS bundling tool is a dashboard. This is basically a visualization component, which allows monitoring the traffic status, the performance of traffic control strategies on traffic, and the end-user acceptance. Thanks to the assessment of key performance indicators and the combined elaboration of control diagrams, digital maps, and historical data. Today, road authorities are engaged with monitoring and measuring the road network and traffic conditions by means of equipment placed on the roadside, and they can influence traffic patterns by providing information through road signs and announcements. But this is generally limited to the mainstream of vehicular traffic. On the other hand, service providers are capable of guiding traffic via personalised travel and routing information provided directly to the driver. Collective and individual mobility management, however, may conflict, resulting in negative impacts on road transport system. The future of traffic management is represented by new cooperative approaches, like the one developed by the Ertico innovation platform, named TM 2.0, which promotes the deployment of a connected, decentralized, and interactive traffic management system, where public and private stakeholders can act together to provide individual, high-quality, profiled routing services, while preserving the collective interests of a safe, efficient, and sustainable transport. What is needed to realize these objectives is understanding among stakeholders, cooperation and mutual trust, alignment and consistency of information provided to drivers. Such cooperation can enhance traffic management by bringing coherence between traffic management plans provided by road authorities and dynamic traffic information provided by traffic service providers and guidance provided by navigation providers. Public authorities, end users, and businesses would all benefit from such interactions. Different levels of cooperation are possible in the frame of TM 2.0, which can progressively enhance traffic management by road authorities while optimizing route guidance for the drivers by service providers. The first level of cooperation between the public and private TM stakeholders, called Level 0, involves only the exchange of traffic management information and incidents by the public sector and floating car data by the private sector, based on which both the traffic managers and the service providers can optimize their own processes. In addition, Level 1 encompasses the possibility to display or discard the strategic route recommended by the public authority after evaluation by the service provider. In this case, the service provider decides to display or not. With Level 2, compulsory display is possible as an option for the public strategic route. In this case, the end user decides whether to follow the recommended route or not. By implementing Level 3, a mandatory takeover of routing by public strategic route is enabled. But in this case, this decision rests with the road authority. Finally, Level 4 encompasses a routing indication that balances the load of traffic on the road network. That allows distributing traffic flows, according to both individual destinations and free capacity slots on different routes. It is clear that the main added value of TM 2.0 deployment is a win-win-win situation for all the stakeholders involved, as they should all be able to realise their mission and objectives. Concerning public authorities and traffic managers, they can avoid congestion and traffic collapse, avoid unnecessary harmful vehicle emissions, improve traffic management plans by complementing or replacing loop detectors and enhancing accuracy, have traffic management plans and measures reaching the individual driver directly, extend traffic management in roads not equipped with ITS roadside infrastructure thanks to floating car data. For the traffic information service providers, TM 2.0 allows them to provide to their users information that goes beyond traffic congestion, provide to their users the best route option for the destination, and not only the fastest. Not only provide information about a problem, for instance a congested road, but also the solution for such problem. That is the indication on the best route. Service providers can do that well in advance by having access to real-time and predictive information made available by traffic management centres. Make regional information available as part of an integrated service. The win for the drivers encompasses the possibility to avoid congestion and therefore have a more relaxed, less stressful driving journey. The possibility to receive relevant regional information in vehicle. The possibility to receive advice about best route options aligned with traffic management plans. And finally, an improved road safety through smoother traffic flow. The demand for urban mobility traditionally depended on private car ownership and usage. This situation most of the time has led to severe congestion issues, poor air quality, and high levels of noise and CO2 emissions. To pave the way towards sustainable transport, the multimodal mobility management aims to support city authorities in optimizing traffic flows, respond promptly to the traffic network's bottlenecks, handle sudden incidents in real time, make more efficient use of the available capacity in different existing transport networks and modes by predicting and adapting to passenger flows variations and needs, and even being in a position to nudge them with incentivization techniques in a common migration path of interactive traffic management and mobility as a service. Indeed, combining TM 2.0 and mass information, data sources, interfaces, and organizational processes, a more comprehensive approach towards multimodal mobility management can be built. This will be focusing on and empowering the efficiency and sustainability of mobility. The Ertico Innovation Platform TM 2.0 and the MAS Alliance are gathering forces from both communities, such as traffic management stakeholders, such as traffic managers, road operators, traffic service providers, OEMs, infrastructure suppliers, and others, local and central governments, city transport network management operators, authorities and operators of public transport on the road, rail or ferry, private mobility service providers, taxi, ride-hailing, ride-sharing, etc., freight and logistics operators, parking operators, travel information and service providers, mass operators. By developing clear business rules and a functioning organizational framework that encompasses a secured data sharing environment, well-defined roles and responsibilities for all the stakeholders and market players involved, knowledge management tools. The cooperation between public and private stakeholders can ensure end-user engagement and realise a higher value win-win-win for public authorities, businesses, citizens and the environment. By doing so, multimodal mobility management will pave a common path towards safe, efficient and pollution-free flow of people and goods, which will provide affordable, accessible, healthy and integrated mobility. Continue training with the other e-learning courses on CITS. Part 1, Introduction. Part 2, Road Users. More on CITS on the C-MobILE project platform, Twitter and LinkedIn. To ensure a successful, large-scale deployment of CITS services, the consortium of the C-MobILE project brings together partners, local stakeholders and road users representing the entire transport ecosystem.